Hi, welcome back to another video on CMOS VLSI design. By the end of this video, you will be able to put together a NOT gate, which is the very basis of all CMOS design, and also appreciate the differences between CMOS, PMOS, and NMOS technologies. We will also have a look into a few applications of the CMOS NOT gate, which include the static RAM cell, which is the fastest memory type used in computers, and also the ring oscillator. It's quite important that you understand how a NOT gate is put together, as all the other gates in CMOS are implemented within this gate. You will find it quite easy to understand what's going on, especially if you saw the last video. So without any further ado, let's get started. Okay, let's recall from the last video where we described both the N and P type MOSFETs. They are both switches and they both need a voltage difference on the gate compared to their source to turn on. The P-type needs a negative voltage difference on its gate compared to its source, and the N-type needs a positive voltage difference on its gate compared to its source pin to turn on. Now, let's consider an interesting arrangement of these two types of MOSFETs in a circuit. Suppose we have a battery with its positive terminal connected to this rail here, and its negative terminal connected to this rail here. We will now insert a P-type MOSFET and an N-type MOSFET. Remember, for the P-type, its source is always connected to the positive rail, and for the N-type, its source is connected always to the negative rail. We will also connect the two drains and the two gates together. What we have effectively created is a CMOS NOT gate. Let's draw this circuit again to investigate why we have a NOT gate. If the gates are connected to the positive rail, like this, the P-type MOSFET is off. Remember, the gate needs a negative voltage difference to its source to turn on, and we currently have 0. So it is acting as an insulator. The N-type, however, is on, since there is a positive voltage bias on its gate compared to its source pin, and is now acting as a conductor, or a wire if you like, effectively connecting this point to the ground. If I now connect the two gates to the negative rail, this type, the N-type MOSFET, is off, whereas the P-type is on, effectively connecting this point to the positive rail. We will call this point the input, and this is the output of our NOT gate. So for any input, we get the negated output when the input is high, the output is low. When the input is low, the output is high. Connecting the input to high, the plus rail, the bottom part turns on, whereas connecting the input to the low or the negative rail, the top part turns on. Since we have these two parts, the P and N parts, turning on and off by complementing each other, we call this complementary MOS, or CMOS for short. Now let's see a NOT gate in the real world. We will use a breadboard for our circuit. For those unfamiliar with breadboards, all these holes on each of these horizontal lines are connected together, and all the holes on each of these columns are also connected together. We have put together an LED indicator circuit to help us see what the output of the NOT gate is going to be. The green wire is the input to this circuit, and if I connect it to the top rail, the top LED turns on. If I connect it to the bottom rail, the bottom LED turns on. The field effect transistors we are going to use is this one. This is a P-type one, and this is an N-type one. Their pins, as you see the transistor head on, is gate, drain, and source. Let's start with putting the P-type transistor in the circuit. We always connect its source to the positive rail. Now let's put the N-type transistor. We always connect its source to the negative rail. And now we'll tie the two gates together so as to form the input to our NOT gate. This purple wire is now the input, and we'll also connect the two drains together so as to form the output. Our NOT gate is now complete, so let's examine its behavior with our LED indicator. If I connect the input of our NOT gate to the high rail, the output is low. If I connect the input to the low rail, the output is high. Note that I can also drive the two transistors with a very high impedance, since we are still using field effect transistors. Now, the benefit of a CMOS NOT gate is that its output is directly connected to either the positive or the negative rails through one of these two transistors. So any following logic that depends on its output can get as much current as it likes, or at least what the MOSFETs can supply. This is all you need to know for now for the CMOS NOT gate. There are two other classes of logic besides CMOS, which are the NMOS and PMOS. What you see here is the NOT gate implemented in CMOS, NMOS, and PMOS. NMOS is when you substitute the P-type transistor to a static resistor. A resistor, for example around 10 kilo ohms, is a worse conductor than a wire, but a better conductor than a good insulator. Its conductivity lies somewhere between the two. In NMOS, when the transistor is off, the output is pulled high by the resistor, since the resistor is a better conductor than a very good insulator. If you turn the transistor on, since it's now a better conductor than the resistor, it will fight the resistor and win, and pull our output low. The PMOS type of logic is when you substitute the N-type transistor to a resistor and works equivalently to the NMOS type. The problem with these types of logic, for example with NMOS, is when the transistor is on, it has to fight the resistor to bring the output low, which means we are spending electricity for the off state. Also, when the transistor is off and hence the output is high, our output signal now passes through a resistor. This means if on the output we have connected logic that draws a lot of current, the voltage will sag as the resistor will not be able to supply the current required, and our logic will just fail. Besides the disadvantages, NMOS and PMOS have a few advantages. One of these is that they require exactly half the amount of transistors to CMOS. Also, with NMOS, we can create a quick and dirty voltage shifter. This might be beneficial to those who want to connect an output of a microcontroller pin to a part of a circuit that works on different voltages. Imagine, for example, the scenario where we want to control a big MOSFET that requires at least 4 volts to turn on, with the output of an ESP32 microcontroller which works at only 3.3 voltage levels. The pin on its own cannot drive the MOSFET as it can only reach 3.3 volts. Putting an NMOS NOT gate in between the pin and our MOSFET, and using a small signal MOSFET here which turns on with merely a plus 1 volt bias on its gate, we can drive the big MOSFET with plus whatever voltage we have put at the NMOS gate. We couldn't do this with a CMOS gate, as 3.3 volts would turn on both the P and N parts of our bridge, effectively short-circuiting the positive and negative rails. The problem where you energize both the P and N parts is called shoot-through. We must always pay close attention to this never happening, or our MOSFETs will produce the magic white smoke. Now that we saw how to implement a CMOS NOT gate, let's see how to put some into good use. One great application of the CMOS NOT gate is the static RAM, or SRAM for short. Since we are talking about memory here, you might be thinking that, well, wait a moment, I just saw the NOT gate retain its state while you had its input dangling earlier on. Cannot we use this as memory? Well, no, because the charges on the MOSFET gates are only stored temporarily, they're quite lossy. and this becomes even worse and worse as the MOSFETs become smaller and smaller. So we do need a mechanism here to help us replenish the charges on the MOSFET gates. This is where SRAM comes into play. SRAM is the fastest memory type in computers, and even the registers are implemented in SRAM within the CPU as they need to be quite fast. To implement SRAM, we just put two NOT gates in series with the output of the first going into the input of the second and the output of the second going back into the input of the first one. This way, one NOT gate reinforces the other NOT gate and the state is kept alive as long as we provide current to the circuit. For example, if we have a high signal here, we'll get a low one here and a high one here, which will reinforce the initial high going into the input of this SRAM cell. Now I have implemented this circuit here, and this purple wire is this input point here. If I connect the input wire to the top rail and disconnect it, now the SRAM remembers the high state. If I connect the purple wire to the bottom rail and disconnect it, now the SRAM remembers the low signal. Another application is the ring oscillator. A ring oscillator simply consists of an odd number of NOT gates, be it 3, 5, 7 or so on, connected in a circular manner as we did with the SRAM. Since we're using an odd number of NOT gates, the last gate state will always have the reversed output of what the input was to the first gate. This makes the circuit oscillate, that is, change states from on to off and vice versa continuously. I have also connected these capacitors here so as to make it really difficult for the gates to be charged, so that the circuit oscillates much slower than it would, so that we can see its action. As we'll see in the next episode, all the other gates are based on the NOT gate. The NOT gate is the smallest, simplest and therefore fastest gate we have in CMOS. That is why when we design a CPU, the first thing we scribe on the silicon is a ring oscillator, so that we do have a reference of how fast our gates can be. Until the next episode, thanks for watching and we'll speak soon.